All right, so in the previous class, we discussed about the Monte Carlo integration, right? Do you have any doubt or any question regarding the Monte Carlo integration? Did you understand the Monte Carlo integration? All right, so we will go further today, okay? And we will discuss about the impotence sampling. This is the another method to generate the random numbers and to solve the integral. All right, when we are not able to solve the integrals by hand, or we are not getting the integrals in the closed form, so at that time we can use this method also. So suppose you have the density function px, all right, and roughly approximate to the density of qx, all right. Then we have integral fx into qx, all right, where qx is our targeted distribution, all right, that we want to solve, all right. The integral with respect to qx we want to solve, and fx is again a function of x, random variable, all right. So in that one we can write it like this: fx into multiply qx, that is the our targeted density, multiply and divide by the proposal density, that is approximate to the equals to your density qx, all right. So at that time what will happen? Now it will behave this one, fx into qx divided by px will behave like a function of x, and px will be your density. And now when you are going to find out the integrate over the range of x, what it will be? It will be the expectation of fx into qx divided by px into with respect to the density of px. All right. So if you are able to do it, or if you are able to write your integration in such form, in the form of given in equation 1, that is called as the impotence sampling method. All right. That was called as the impotence sampling method. Here what we were doing in that one, in the Monte Carlo integration, we had the only the function of hx. We didn't have any density earlier. All right. We didn't have the any density. So at that time we were writing this function hx equals to the fx into px. All right. So we were writing this function into the term of the function and PDF. Right. So you can say that impotence sampling is the generalization of Monte Carlo integration. Okay. Because in this one, they are already providing you a one density function, that is your qx. So you need one density function here. Here you need a one density function that is approximately similar, or you can say can overlap your qx. All right, density qx. So you need one density function that you need to choose here. All right. So in this one, this form basis for the method of the impotence sampling with integral fx into qx with respect to x is approximate to the 1 upon n summation I goes to 1 to n fx I into qxi divided by pxi, where xi follows the distribution x px. Means what you need to do right now to solve this integral, okay, to solve this integral, you need to generate the values from the px. You need to generate the value of x from the px, and then you need to keep these those values into these three functions fx, qx, and px, and for large n, you need to find out the average. Okay, so that will be equivalent to your integral of fx into qx dx. All right. So if we are interested in a marginal density function, here we are taking the example, in the marginal density function of y, then the integral jy equals to integral of fy given x into qx dy. We need to find out this one. Okay. So then what we will do, we may approximate this density function jy equals to 1 upon n summation I goes to 1 to n fy given xi into qxi divided by pxi. What is the marginal? Marginal means you already know the other variables, right? So you need to solve this integral. So here, if you put the values of xi in this function, that will remain the function of y only, and then xi values are here and pxi values are here, so that will be the constant for the known parameters, and then simply you can get the marginal distribution value for your y. All right, here we are going to take the one example. Okay, now consider x follows the Weibull distribution with parameter beta and 1. Okay, that means we are the parameter k we are going to assume is known and it is equals to 1. Fine. In the Weibull distribution, we have two parameters. Correct? K and beta. So we are assuming k is given equals to 1. So what will be the density function at that time of Weibull distribution? Beta into x raised to the power beta minus 1 into e raised to the power minus x raised to the power beta. Correct? That should be your density. You can compare your density with your previous example. All right. So here we are assuming that the prior distribution of beta is 1, that is uniform, basically. All right, for given beta is greater than 0. So how you will find out the posterior density function here? The likelihood of your experimental distribution into the prior. So what will be the likelihood of this one? Beta raised to the power n, product of xi raised to the power beta minus 1, right? E raised to the power minus summation xi raised to the power beta into 1. In the denominator, the same thing will be there, right? And only you need to integrate over the range of beta 0 to infinity, right? So can you solve this one, this integral? Can you solve this integral? You need to solve this integral with respect to beta. So beta is there, then in the product xi raised to the power beta minus 1 is there. Again e raised to the power minus summation xi raised to the power beta is there. Can you solve this integral? Not at all, right? You cannot solve this integral at all. So what you will do, you need to approximate this one right now to find out the posterior density function, right? So here what we are doing, if you are not going to solve this integral, so you cannot find out the posterior density function, right? To get the posterior density function, first you need to solve this one, and after that to find out the Bayes estimate, you need the posterior density. If you don't have the posterior density, how you will find out the Bayes estimate, right? So in that one, if we are considering the Bayes estimate under the self, how you will find out the Bayes estimate under the self? You will, this is the constant term after integrating with respect to beta, right? So it will come out from the integral, only the numerator part will remain, right? Correct or not? In that one, you need to multiply by beta and then the density, remaining portion of the posterior density, and integrate again with respect to the beta. Right? That you need to do. Yes or no? So here, what I am going to do, beta raised to the power n. So I am replacing it with the beta raised to the power n plus 1. Are you getting this point or not? I think he is not getting. Are you getting or not? Not at all. Okay. So we will do this thing. See, here you have the posterior density, that is beta. Is it visible for you? Right. Beta given x curve. That is your beta raised to the power n, product of I goes to 1 to n, xi raised to the power beta minus 1 into e raised to the power minus summation over the range of I, xi raised to the power beta. Okay, because you need to multiply by 1, so I am not going to write it because it will not impact at all. So now integral over the range of beta, beta raised to the power n, product of I goes to 1 to n, xi raised to the power beta minus 1 e raised to the power minus summation over the range of I, xi raised to the power beta d beta. Right. So now we have seen that till now, when you are going to solve this integral, it will be a constant term. Yes or no? The denominator part. Because xi is known, xi is a numerical value. Yes or no? Okay. When you are going to integrate over the range of beta, and beta, if beta is known, you will get the value of beta, you will put the some value of beta. So what else will be there? Any variable will remain? There are only two variables, x and beta. If I will provide you the value of beta and x, it will be a constant value. All right, so I can write it as, say I am saying it 1 upon b. This is your b equals to b, right? So now it is beta raised to the power n, product of I goes to 1 to n, xi raised to the power beta minus 1 into e raised to the power minus summation over the range of I, xi raised to the power beta. Correct or not? That will be your posterior density now. Correct? This is your posterior density. Right? And the Bayes estimate, okay, the Bayes estimate under the self. What is the Bayes estimate under the self? The posterior mean, right? That is expected value of beta given x curve, right? So what it will be? Integral over the range of beta into beta, sorry, not into, beta into beta raised to the power n into product of I goes to 1 to n, xi raised to the power beta minus 1 into e raised to the power minus summation over the range of I, xi raised to the power beta d beta, and 1 upon b will come out from the integral because it's a constant term, right? Now you have this portion, so I can combine beta and beta raised to the power n. Base is same, so what it will be? It will become, that will becomes beta raised to the power n plus 1. The same thing that I wrote here. Okay, beta raised to the power n plus 1 product I goes to 1 to n xi raised to the power beta minus 1 e raised to the power minus summation xi raised to the power beta d beta. And this 1 upon b I am writing in terms of integral only. Okay, because I cannot solve it in the closed form. All right. So now, suppose here we are going to suppose that beta is following the exponential distribution, standard exponential distribution with parameter 1. Okay, theta is equals to 1 here. We are taking theta equals to 1. Okay, so what will be your density then? E raised to the power minus beta. Correct. What is the exponential distribution? Theta into e raised to the power minus theta b, or theta into beta. If I am going to take theta equals to 1, it will becomes 1 into e raised to the power minus 1 into beta. So that means it is equals to e raised to the power minus beta only. So I am approximating my beta is following exponential distribution, because what is the distribution close to your variable? What is the distribution that is close to your variable distribution? Exponential. Exponential is the particular case of variable distribution or not? If I am putting here beta equals to 1, if in this density, if I put beta equals to 1, what it will becomes? 1 into x raised to the power 0, 1 minus 1 into e raised to the power minus x raised to the power 1. So what it will be equals to? E raised to the power minus x. So what it will becomes? Standard. This density, it will becomes standard exponential or not, right? So I can consider the beta is also follows the standard exponential distribution here, right? So after that, what I will do? I am going to multiply and divide by e raised to the power minus beta in denominator and numerator. Okay. In the both places, in the denominator and numerator, I am going to multiply and divide by e raised to the power minus beta. Right. So here, consider this portion together. This one. Beta raised to the power n, product of xi raised to the power beta minus 1, e raised to the power minus summation xi raised to the power beta divided by e raised to the power minus beta together into e raised to the power minus beta. In both places, in the denominator and numerator, at the both places, just take these together. Sorry, these together. Right. So now what it will becomes? Are you getting this point or not? Wait, X one. Why we are doing? Why we are introducing? Right. Why we are introducing? First of all, we were taking this one. Variable distribution was our experimental distribution. Corresponding to that, we were taking the prior one. Okay. After that, we need to find out the posterior density. Okay. Now, I asked you earlier, can you solve this integral? The denominator part. Can you solve it in the closed form? No, you cannot solve it in the closed form, right? After that, if you cannot solve this denominator part in the closed form, so can you find out the posterior density in the closed form? Posterior density is not in the closed form right now. So can you find out the Bayes estimate in the closed form right now? Not at all, right? So now we are going to use the importance sampling. What was the importance sampling was saying? Importance sampling was saying that if you have integral in the form of fx into qx, where qx is your density function and fx is the function of x. Okay, fx is not a density, is the any function of x, right? So at that time, if you can find out some density function that is your px, that is roughly approximate to your given density qx, if you can approximate, okay, if you can approximate your density qx with the px, so at that time what we will do, we will multiply and divide by this density, and at that time what will happen, when you are going to divide and multiply, okay, so now keep this term fx into qx divided by px at a one side and take it as the multiplication, this density. So now what it will becomes? It will become the expectation of fx into qx divided by px or not? Yes or no? Are you getting this or not? How we get the density? How we get the expectation? Also, yeah. See, how we get the density? Oh, sorry, expectation. How we get the expectation? Expected value of x if x follows the density fx. What will be your expectation? Integral x into fx dx. What is the expectation of gx? Integral gx into fx dx. That is the expectation formula. Yes or no? So what we are doing here? We are taking this entire function as a one function, say gx. So now it is basically what? Integral gx into px dx. Px is your density of your x. Px is the density of your x. So now it will becomes the expectation of gx, or your gx is fx into qx divided by px, right? So the same thing we are going to do here. We have the integration in the denominator, right? And when you are going to find out the estimate, so at that time you need to multiply by beta and integrate over the range of beta in the denominator also, that I showed you here, right? I showed you here that 1 upon b integral, right? So I think you should not have any confusion here in this portion. So after that, what we are doing, I told you if I'm going to put here beta equals to 1, k equals to 1 and beta equals to 1, so your Weibull distribution is going to reduce to the standard exponential distribution, right? So that means your beta is approximate to your exponential distribution. I can approximate it with this, right? So that's why I'm saying that p beta is equals to a raised to the power minus beta. I'm assuming, right, that standard exponential distribution. And after that, what I am going to do, because I need this form, I need this form fx into qx divided by px. All right, how I will get this one? I need to multiply and divide by e raised to the power minus beta in the numerator and denominator both, right? Because I can cancel out this one, it will not make any impact, right? So after that, what I will do, I am having the density function, because e raised to the power minus beta is a standard exponential distribution. So I am going to consider this one, this portion, as a fx into qx divided by px, and this is my px, that is the exponential distribution, right? And again this one in the denominator part, the similarly in the denominator part, this part is my fx into qx upon px and multiply by px. So what it will be? It will be the expectation of beta raised to the power n plus 1 multiply by xi raised to the power beta minus 1 into e raised to the power minus I goes to 1 to n xi raised to the power beta divided by beta e raised to the power minus beta and divided by expectation of e raised to the power beta raised to the power n. Okay, so now here in the numerator you have n plus 1, in the denominator you have only n. All right, and beta follows the exponential distribution, so you can approximate like this. So for that one we have one R code here. Okay, for the same example. Is it visible for you? So what we are going to do here, we are assuming beta 2, beta is the true value of the beta is 2, all right, and we are going to generate only 6 values of our random variable that follows the variable distribution, all right. You can increase these values also, say 20, all right. So how you will generate the random values? R variable size n, true value of beta, scale is equals to 1 because we took the k equals to 1, right? So we are going to generate these random numbers. Okay, this is my random numbers. Wait a second. Okay, this is my 20 random numbers. Now I am going to run the Monte Carlo sample size of 50,000. Okay, how many times I can repeat it? Because here in this one, what is there? It was 1 upon n summation I goes to 1 to n, means how many times I am going to do the repetition. Okay, Monte Carlo repetition. So that this n is 50,000. Okay, that n that I am writing here, that is different. This n is different. Okay, this n is different. After that, what I am going to do, I am going to generate the beta from the exponential distribution. Okay, with parameter 1 and 50,000 beta I am going to generate because I need to keep these 50,000 values in this function. Okay, I need to keep my values of beta here. Right, now this is the distribution of beta. I have only 20x. X is my experimental observation that is given to me. Okay, I am doing a simulation study, so I am taking the 20 generating, I am generating 20 values. Otherwise, it is given. Now I need to generate the beta again and again from the exponential distribution, and I need to keep that value in this expression, this complete expression. Okay. So after that, what I am going to do here, initial sum I am going to take 0 because what I need to do, I need to take the mean. In that one, what I need to do, I need to add all the observations one by one. That's how you apply the for loop, right? When you find the mean, how you find out the mean in the R? How you will apply the loop if you want to find out the sum? I told you earlier this one. When you find out the sum, how you find out the sum in R? How do you find out the sum in R? By using the for loop. If I am saying I need to add 1 to 10, how you will add in R? You need to define x equals to 0. So 0 plus 1, 1 and then 1 will replace this 0, and then it will becomes 1 plus 2, that is your 3, then 3 will replace this 1, and then 3 plus 3 is equals to 6, and this 6 will replace this 3, initial value 0, and then 6 plus 4 is 10, and this 10 now will replace this 6, initial value 0, and then 10 plus 5 equals to 15, and so on. That's how you do. So you need to start from the 0, right? Correct or not? Right. So the same thing we are going to do here. We are starting from the 0 because we need to take the sum of the numerator and denominator. Okay. So here what we are going to do, we are going to apply the for loop from 1 to n. N is our 50,000 iteration, and then we are going to put all 50,000 observations here in the beta, in B, and after that what we are going to do, before that one, we need to find out the sum and the product of xi, because 20 xi is there, right? Every time we need to multiply these 20 observations or not. Here, if you just see here what we are doing, you will put the one value of beta here, but for that you need to multiply 20 times of your xi, yes or no? And then you need to find out the sum of xi also, right? After that, for the second value of beta, again you need to multiply this one because it will change every single time because beta is there in the power, yes or no? So this product and this sum will change every single time, right? So for that one, we are applying this one for sum xi, sum of xb, that starts from the 0, okay, that starts from the 0, and then xi raised to the power b, okay, that beta that every single time I'm going to generate, okay. This loop will close, and now this is the loop for the product of xi. So when you are going to multiply, you need to start with the 1. If you will start from the 0, so all the observations will be 0. So that's why you need to start from the 1 for the multiplication. So that's why we are taking 1, and then we are going to find out the product, xi raised to the power beta minus 1 here. Okay. Now after that, what we have in the numerator and denominator? We have beta raised to the power n plus 1. So b raised to the power n plus 1. Right? Then we have product of xi raised to the power beta minus 1, that we are going to save in product x. Alright. After that, we have e raised to the power minus summation xi raised to the power beta, that is exp. Alright. Summation raised to the power xi minus beta. Right. And in the denominator, what we have? Beta raised to the power n, and other terms will remain as it is. Right. Product of x part and e raised to the power minus sum of xb. So we are going to find out the total sum because we are running 50,000 times. So here in the numerator sum, it is numerator sum plus numerator term. Okay. That is your numerator term, and numerator sum was start from the 0. So everything should be accumulate in the numerator sum only, right? And the similarly for the denominator, right? After that, what we are going to do, we are going to find out the beta hat, that is your estimate of beta here. Beta hat is your numerator sum divided by the denominator sum, and that will be your posterior mean. What happened? 1.77. That is close to your 2. Alright. If you will increase the iteration here, or you increase the sample size also, So at that time you will get approximate to 2. All right, if I am going to do it, suppose 100,000, it is still one. Okay, I am not changing the sample size. Set dot seed, and I am going to increase it up to 100. Okay, it will take a bit time. 2.01 means almost 2. If you will increase the sample size as well as you will increase the number of iteration, you will get the exact value of, not exact, the approximate true value of your beta. Beta we took 2, and right now it is 2.01, right? So this is the code of your, that one, what we call it, importance sampling for this given example. All right. So do you have any doubt in this one, in the importance sampling? Did you get the importance sampling? Where you are getting the problem? Let me know. This is your importance sampling method. I didn't get, please. Okay. So if you have any doubt, you can ask me anytime. All right. So this was your method, that one, importance sampling method, and we already discussed the inverse TDF method. So now we will move to the some other methods. So importance sampling, in that one method, in after that we had the inverse CDF method. For inverse CDF method, we need the CDF in the, means we need the F inverse U in the closed form. Okay, we need that one was in the closed form. So at that time, what we do, if we are not able to do that, we use the other methods like accept reject method, metropolis algorithm, and metropolis hasting algorithm, and or gift sampler. Gift sampler we already discussed. So now we will discuss the accept reject algorithm. Okay. So what is the accept reject algorithm? That we use to generate the random sample. Okay. So let fx be a PDF of your random variable x. So if they are giving you that x follows any distribution fx, and y is a random variable that follows another distribution gy. Okay, sorry. Y follows gy. Alright, here fx is called as the target PDF and gy is called as the instrumental or proposal density function. Alright. And after that, use a random variable that follows the uniform distribution. So here you need the three distributions, and u follows uniform distribution between the range 0 to 1. So where y and u are independent. Okay, y and u should be independent and for some constant m. So here, if you have the relation fx is less than equals to m into gx, that means if you are going to plot the density function, that this is the density function, this dots are the density function of your fx, and after multiplying by constant m, gy is going to completely covering the fx. All right, so you can use m into gx to generate the random values for fx. Okay, if you have any proposal density gx that is going to cover the complete density function of fx, then you can use gy to generate the values of x. How you will use that one? So in that one we have three steps of algorithm. So first of all, you need to generate y from gy, density function gy, and u from the uniform distribution from the 0 1. After that, you need to find out this relation u should be less than equals to fx divided by m into gx. if this condition is going to be satisfied, means after dividing the density function fx divided by mgx, the difference should be less than 1, because when you are going to generate the values from uniform distribution between 0 to 1, what is the random values will occur? What are the random values that will occur? Between 0 to 1 means that should be less than 1. Alright, if u is this 1, whatever the difference you are taking, that is less than or equals to fx divided by the m into gx, then you will take x equals to y, otherwise you will return to the step 1. Again you will generate the values from gy and uniform, and again you will check this condition, and then you will take the random sample, and then x will follows the pdf fx. Okay. Are you getting this point? So in that one, there is a proof of this theorem is that if you are going to, if I am going to provide you that find out the distribution function of x, what is the distribution of function of x from here? The marginal CDF of x, that will be probability that y should be less than equals to x. Okay, from there x should be less than equals to y, right? Y should lie here, given that uniform u should be less than equals to fy divided by the m into gy. So how you will find out this probability? Conditional probability, that is the conditional probability. So that will be probability y less than equals to x intersection of u less than equals to fy divided by m into gy, divided by the probability of u is less than equals to fy divided by the mgy. Here we are saying that u and y both are independent. If both of them are independent, so this intersection you can write in the terms of multiplication. If u and y both are independent, so integral can be written as in the term of, both terms can be written in the multiplication. So here y is less than, so that is basically probability y less than equals to x into probability u less than equals to fy divided by m into gy, right? This is in the multiplication. So what is this? How you will compute this one? Integral minus infinity to x, right? Gy integral with respect to the y, and then how you will find this one? Because it is from the uniform distribution between 0 to 1. What will be the PDF at that time? 1 upon b minus a, that is 1 upon 1 minus 0, so it is 1. So that's why we are writing integral 0 to fy divided by m into gy into 1 du. So when you are going to find out this integral, what it will be? It will be u, right? And when you will put this limit 0 and fy divided by m into gy, what it will be? Fy divided by m into gy minus 0. So what is the remaining term you will have? Fy divided by m into gy into this gy in the numerator and denominator both. Yes or no? Are you getting or no? Okay. I am saying that I am saying that you have you need to find out the probability x is less than equals to x, the marginal that you need to find out. So for that one you have probability y is less than equals to x, given that, right, u is less than equals to fy divided by m into gy. All right. So this is the conditional probability. Yes or no? This is your probability A given B. So what is the formula of probability A given B? Probability A intersection B divided by probability B. Correct? This is the formula of conditional probability. Apply this formula here. So what it will be? This one. It will become probability y less than equals to x intersection u is less than equals to fy divided by m into gy, right, divided by probability u is less than equals to fy divided by m into gy, right. Now you need to solve these probabilities. How you will solve these probabilities? Here in this algorithm we assume that y and u both are independent. So if probability of A intersection B, if both of them are independent, how you will write this? How you write this one? Probability A into probability of B, right? So similarly we are going to use here, so it will be basically probability y less than equals to x into probability u less than equals to fy divided by m gy divided by probability of is to fy. This was fy, no? Right. M into gy. Right. Both of them are independent, so you can use the now. If you are going to use the integral sign, so you need to first of all for this one, you need to integrate this one. So what it will be? 0 to x, right? Gy dy, right? Inside that one, sorry. So how? So how you will do that? It is for integral. Now this is the second integral for 0 to fy divided by m gy for 1 into du, and first you need to solve it because here also y is involved in this one. If two integrals are there and y is involved in this one also, so first you need to solve this integral. Correct? Gy dy divided by integral over the range of 0 to fy divided by m into gy 1 du. So what it will be when you are going to solve this integral? Integral of 1. It will remain u, right? So you have u, and what is the range? 0 to fy divided by m into gy. What it will be when you will put the limits? Fy divided by m into gy minus 0. So that means it will remain as it is. So if you will put it here, so what it will be? Integral 0 to x fy divided by m into gy into gy dy. Which one?
The wording is supposed to be there.
Here?
Oh, for the last one.
This one? See, we took here minus infinity, right? So either you, why we took the minus infinity here? Because we don't know what is the exactly gy.
Right, which ones?
Yeah, so we can put here minus infinity or 0. Anything we can put because we don't know what is the distribution exactly. So for safer side, what should be the generalized limit for the any distribution in the statistics? In the statistics, what should be the general limit for any distribution if you don't know the distribution? Minus infinity to infinity, because distribution cannot be defined on the complex plane, right? So that's why we are taking here minus infinity, because we don't know what is the exactly our gy distribution. All right. But if we assume that it is from no, it is a lifetime distribution, that is start from the 0. So at that time we can take it from the 0. All right. So you can take it as the minus infinity also. Right. So when you are going to multiply it, so it will be cancel out. Gy will cancel out from here. All right. So now after that, what you will remain only? Integral minus infinity to minus infinity to x fy dy. All right. So and in the denominator, it is minus infinity to infinity fy, because why we are taking minus infinity to infinity here? Because when you are going to solve this one, you need to solve the, first of all, you need to make it free from y. How you will make it free from y? When you are going to integrate over the range of y, how you will make this term? That is your fy upon this one, where you have the independent uniform distribution that you want to find out. You should be less than equals to fy divided by the m into gy. How you will find out this one? First of all, you need to find out the you need to solve this integral, but in this integral you have already gy, right? So how you will make it independent? For that one, you need to integrate over the range of y. So that's why we have minus infinity to infinity here. All right. So when you are going to find out the this integral minus infinity to infinity, that should be 1, and what you have here minus infinity to x fy. So that is basically CDF of fx, CDF of x, right? So that's how you get the density function of fx. All right, in that one, what we do, if you just see here, basically in the R programming, yes. So I'm going to use this R programming to generate the random numbers. Okay, so what I'm going to do here, I'm going to generate 100 random numbers. Okay, and I'm going to take the value of parameter a equals to 2 initial value, and theta I'm going to assume equals to 5. That is basically for uh, a is basically my constant here, right? Sorry. Not a is not a constant. I'm not going to use that one. That was something else. Okay, what I'm going to do, I'm going to generate 100 random numbers, and theta I'm going to assume is 5, and because I need to store the value, so I'm going to start from the 0, and here I'm going to store the value in c equals to my empty vector. Here what I'm going to do, I'm going to generate the n numbers from the uniform distribution from the range 0 to 1. Okay, that is my u, because every single time I need to repeat this one if I am going to where here. What I am going to do here, I am going to generate the one value of y from the gy and one value of u from the uniform distribution to generate the one value of x here. Okay, correct. So I need to generate 100 observations. So for that one, I need to generate 100 observations of u from the uniform distribution and 100 observations of y from the gy. Correct. If I want to generate 100 values of x, so at that time, I need to generate the 100 values of u from the uniform distribution. What I'm going to do it, I'm going to generate, I'm going to take my one distribution as a exponential distribution. One distribution I'm going to take as the variable. Okay. Sorry, Ram.
Take X to be down column there.
Where?
X to be C, right? That's
Yeah.
column, the empty column to store the values, right?
Right.
And that previous will be used in numeric. Is it equivalent?
No, both are same.
Same.
See, either you can simply write x numeric. Okay, that is also fine. Or you can simply say x, that is also one way, replicate 0, comma n. Okay, so means n zeros are there. Okay, in this one n zeros are there in your vector, and after that what will happen if you will just run it? So you will find that, oh sorry, so 100 zeros are the, whatever 100 or how many? Sorry, no, I took earlier different one. So n is 100, so now it will change. These are the 25 observations. I don't know. Okay, so when I'm going to I'm going to generate the values of x. So every time 0 will replicate from those values. Okay, so these are the different ways to store the values. Okay, usually we use either this one or this one most of the time. Okay, and mostly I prefer this one, blank, because what happens here, I am already providing the 0 in the x. So if by mistake I am not getting the accurate value or something, or 0 will remain here, so or the size of the sample will change, so some 0 will remain in x, so at that time it will impact my final result. So mostly I prefer this one, the blank vector. Okay. in this blank vector, the benefit is that if you just remember in that one, in the previous example where we took the numeric and as well as we took the one other thing also, numeric and that what is the next other thing that we took for the position? No, no, no. For the numeric is basically for the that one continuous, and for continue for the discrete we took something. I'm forgetting what we took. So here, if you are going to introduce only blank vector, so you can store any value here. You don't need to describe. Okay. So what we are going to do here, we are going to compare. See, if you just see exponential and gamma, so we are generating the some random numbers and random numbers from exponential and random numbers from the gamma that we are storing in the V and W. All right. So what is basically we are doing here? Exponential is basically the particular case of the that one. Wait a second. This is the right code or not? I'm confused a bit. If I equals to ui is equals to theta upon 1 plus theta. No, 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 no. This is not the correct one. Let me check another one. This is for some other. Uh, Let me stop the recording.